Large language models can execute complex, multi-step tasks with near-perfect precision as long as they stay inside the maze we built for them. Recently, open-source models trained via supervised fine-tuning and reinforcement learning have achieved tool invocation proficiency that directly rivals proprietary systems like GPT-4. But this success relies on a critical assumption: a closed environment. The rules, the API endpoints, and the interaction logic remain completely identical between the training data and the final test. Looking at this chart, you can see both SFT and RL training paradigms driving agent performance steadily upward, eventually converging on a flawless success rate. For a systems engineer, this graph looks like a solved problem. The models appear highly capable and stable. But real-world deployments are fundamentally non-stationary. The moment these highly trained agents leave the safety of the static benchmark, that perfect mastery instantly disappears. In the open world, APIs deprecate, data schemas evolve without warning, user instructions arrive riddled with ambiguity. Let's trace how a language model actually executes a task. It builds a chain. A query leads to a tool, which returns an observation, which informs the choice of the next tool. In a live environment, disruptions can hit any point in this chain. User queries shift, action spaces change, unexpected error codes appear, and entire task domains migrate. If an agent fails to adapt to an unexpected return value early in the sequence, that single misstep enters its history state. The error propagates, corrupting every subsequent decision until the system crashes. To measure this exact vulnerability, researchers built the OpenAgent framework, a controlled sandbox designed to inject these real-world disruptions systematically. When pushed into this sandbox, both SFT and RL models suffer catastrophic degradation, but they don't fail in the same way. Their divergent failure modes expose the deep structural flaws in how we train them. We can set up a clinical diagnostic using two trained models. On the left, a supervised fine-tuned agent. On the right, a reinforcement learning agent. We start with Tier 1 of the sandbox, perception. This evaluates how an agent grounds its actions in actual meaning, focusing on scenarios like the semantic trap and identity erasure. The test alters a tool's surface name, injecting random noise or renaming it entirely, but leaves its functional documentation intact. The tool still does exactly what it used to do. Look at the SFT agent's performance. Under cosmetic tool name changes, accuracy collapses and error rates spike. The pathology is symbolic anchoring. The SFT model acts as a rigid string matcher, memorizing associations between names and contexts rather than understanding the underlying logic. The RL agent survives this test. Because its optimization is driven by a reward signal, it is forced to actually read the functional documentation to figure out what the tool does. SFT acts as a superficial pattern matcher. That renders it brittle to the routine cosmetic changes inherent to real-world software. Next, we move to interaction. Think of a mechanical gear grinding against a steel block, unable to reverse course. This is the tool redirection test. It evaluates how an agent reacts to environmental feedback that interrupts its plan. The agent issues a command, but the environment returns an explicit message stating that tool A is deprecated and instructs the agent to use tool B instead. The SFT model reads the deprecation notice, but treats it as a success confirmation. It actively hallucinates a positive result to continue its pre-planned trajectory. The RL agent, however, successfully parses the negative instruction, breaks out of its loop, and migrates to the new tool. We can trace SFT's hallucination directly back to its training data. The optimization objective relies exclusively on clean demonstrations, where observations always validate the previous action. SFT is an open-loop system. Because it has never been trained to update its belief state from negative feedback, it simply ignores reality and blindly executes the next memorized step. So far, RL seems far more capable. But Tier 4 of the sandbox, internalization, exposes its critical vulnerability. This is the fatal error test. A required tool crashes permanently. There is no alternative tool. The task is logically impossible to complete. As expected, the SFT model ignores the crash entirely. But the RL model successfully reads the error and notes that the tool is unavailable. But the RL model makes a dangerous decision. Instead of routing to a refusal state, A reward mechanism pulls the agent toward fabrication, inventing a fake answer. This boundary blindness is caused by a teleological bias in its optimization formula. The training reward presupposes that every single problem has a solution. The policy learns that outputting an answer yields high rewards, while halting does not. While RL adapts better to friction, its structural bias to succeed at all costs prioritizes completion over truthfulness. In an unpredictable environment, this guarantees hallucinations. Both paradigms fail because of the environments they are exposed to during training. Think of the training data as this single, narrow path. Standard SFT optimization draws all of its training histories exclusively from successful, uninterrupted executions. This confines the learned policy to a highly constrained manifold. It never sees error states, ambiguous feedback, or symbolic variations during training. We cannot expect true reasoning if we only optimize for perfect outcomes. To handle chaos, the model must be explicitly exposed to it. To fix the models, we have to weaponize the training data itself. We need to inject failure directly into the learning trajectory. This intervention is called perturbation-augmented fine-tuning, or PAFT. Unlike standard data augmentation that just alters the initial input, PAFT operates mid-trajectory. It actively disrupts the agent's sequence while it is working. We introduce environmental feedback perturbations, like fake API deprecations. The model dynamically routes around the obstacle, learning closed-loop recovery. We also introduce solvability boundary perturbations with a fatal error. Instead of routing around, the trajectory explicitly terminates at a safe halt state, learning task refusal. The quantitative impact is severe. In fatal error scenarios, applying PAFT to an SFT model drives its correct refusal rate from near 0 to over 99%. By decoupling the model from shallow pattern memorization and training it to process negative feedback, we move away from brittle, static systems and toward agents capable of crossing the unpredictable terrain of the open world.